let yourself settle in now. Find that space where your body feels truly supported, where every muscle can release its hold on the day. Take a slow breath, feeling the cool air flow in, and as you exhale, imagine any lingering tension dissolving like mist in the morning sun. Tonight, we're embarking on a journey across the cosmos, but this journey requires no effort from you. Simply let your eyes close gently, or allow them to rest on some distant, unfocused point. Let the story carry you, washing over you like gentle waves lapping at the shore. We're going to explore something that exists at the very edge of comprehension, an object so massive and so powerful that it challenges our deepest understanding of nature itself. But don't concern yourself with memorizing facts or following every detail with precision. Instead, allow the words to paint pictures in your mind, visions of cosmic grandeur that stretch far beyond the boundaries of everyday experience. This is a story about the universe at its most extreme, about light that has traveled for billions of years to reach us, and about a black hole so enormous that it could swallow our entire solar system and still have room for more. So, breathe deeply, let your thoughts drift, and together we'll float through the darkness toward the monster at the edge of the universe, standing before the infinite. There are moments in life when we're confronted with something so vast, so incomprehensibly large, that our minds simply cannot grasp its full reality. We might stand at the edge of the Grand Canyon and feel dwarfed by the immense chasm stretching before us, or look up at a clear night sky far from city lights and feel ourselves shrinking beneath the weight of all those distant suns. These experiences give us a taste of cosmic scale, a fleeting glimpse of how small we are in the grand scheme of things. But even these humbling moments barely scratch the surface of the true immensity that exists beyond our blue marble of a planet. Tonight, we're going to explore an object that makes the Grand Canyon look like a tiny scratch in the dirt, that makes our entire solar system seem like a grain of sand on an infinite beach. We're going to journey across billions of light years of space to encounter TON 618, a quasar powered by what may be the largest black hole ever discovered by human astronomers. This isn't just a story about size for the sake of size. It's a story about the extremes of nature, about the most powerful forces in the universe, and about how humanity's curiosity has allowed us to peer back through time itself to witness cosmic violence on a scale that defies imagination. When we talk about TON 618, we're talking about an object so bright that it shines with the combined light of 140 trillion suns. We're talking about a black hole whose event horizon, that point of no return where not even light can escape, could fit 11 of our solar systems comfortably inside it. We're talking about a cosmic engine that devours the equivalent of several suns every year, converting that matter into energy with an efficiency that makes nuclear fusion look like a flickering candle. But perhaps most remarkable of all, we're talking about an object so distant that when we look at it through our most powerful telescopes, we're not seeing it as it is today. We're seeing it as it existed more than 10 billion years ago, when the universe itself was less than a quarter of its current age. The light we detect from TON 618 began its journey across the cosmos when our galaxy was young and wild, when the very atoms that would eventually become Earth were still scattered among the stars. That light has been traveling through the expanding fabric of space for longer than our planet has existed, carrying information about conditions in the early universe, about the formation of the first massive black holes, about the violent adolescence of the cosmos itself. To truly appreciate Toan 618, we need to build up our understanding gradually, starting from the familiar and working our way outward into the incomprehensible. We'll explore the history of how this cosmic monster was discovered, learn about the nature of quasars and the supermassive black holes that power them, contemplate the physics that governs these extreme objects, and consider what TON 618 tells us about the universe's past and future. Along the way, we'll encounter concepts that strain the limits of human imagination, scales so vast that numbers lose their meaning, and phenomena so bizarre that they seem to belong more to science fiction than to science fact. So, settle in, relax, and prepare yourself for a journey to the edge of the observable universe and the depths of cosmic mystery. We're about to meet the monster. The discovery. When stars weren't stars. Our story begins not in the distant cosmos, but here on Earth, in the high desert mountains of Mexico during the 1950s. The Tonantzintla Observatory, perched on the slopes about 11 kilometers west of Puebla and 33 kilometers east of the Popocatépetl volcano, was conducting a systematic survey of the night sky, photographing and cataloging objects that appeared as faint blue stars scattered across the heavens. This was painstaking work, requiring long exposure times through the telescope and careful examination of photographic plates to identify and classify each point of light. Among the thousands of objects recorded in this survey, one particular point of light caught the attention of astronomers Braulio Iriarte and Enrique Chavira in 1957. They were searching the constellation Canes Venatici, the hunting dogs, looking primarily for white dwarf stars that lie away from the plane of the Milky Way. Using the 0.7-meter Schmidt telescope, they captured images of a faintly shimmering object that appeared decidedly violet, with an unusual blue tint that made it stand out from the surrounding stars. They designated it entry number 618 in the Tonantzintla catalog, giving it the designation TON 618. To the eye, whether looking through a telescope or examining a photograph, TON 618 appeared to be nothing particularly special. It was a blue-tinted point of light, perhaps slightly unusual in its color, but otherwise indistinguishable from countless other stellar objects in the sky. The astronomers catalogued it, noted its peculiar hue, and moved on to the next object. They had no way of knowing that they'd discovered one of the most extraordinary objects in the entire universe. But appearances, as we so often find in astronomy, can be profoundly deceiving. What Iriarte and Chavira had discovered wasn't a star at all. They didn't know it at the time, couldn't have known it, because the very concept of what TON 618 actually represents hadn't yet been developed. The year was 1957, and humanity was on the cusp of a revolution in our understanding of the cosmos. A revolution that would reveal objects so powerful and so distant that they would challenge every assumption we held about the universe. To understand what TON 618 truly is, we need to jump forward to the early 1960s, to a different observatory on a different continent, where another astronomical mystery was about to be solved. At the Palomar Observatory in California, astronomers were grappling with a puzzle that had emerged from the relatively new field of radio astronomy. Radio telescopes, which detect not visible light but the much longer wavelength radio emissions from cosmic objects, had identified several mysterious sources that didn't seem to correspond to anything obvious in the sky. These radio sources were given designations from something called the Third Cambridge Catalog, abbreviated as 3C. One of these sources, 3C273, was particularly puzzling. When astronomers pointed optical telescopes at the position of the radio source, they saw what appeared to be a fairly bright star, with a curious jet of material extending from it. But when they examined the spectrum of this object, breaking its light down into its component wavelengths like a prism separating white light into a rainbow, they encountered something baffling. The spectrum showed emission lines, bright signatures of specific elements like hydrogen, but these lines didn't appear where they should be. They were shifted toward the red end of the spectrum, displaced from their normal positions by an amount that didn't make sense if this were an ordinary star. This is where Martin Schmidt enters our story. Schmidt was a Dutch-born astronomer working at the California Institute of Technology, and in February 1963, he was examining the spectrum of 3C273, trying to make sense of those peculiar emission lines. He had been staring at this spectrum on and off for weeks, running through every possible explanation he could think of. Then, on February 5th, sitting in his office after lunch, something clicked. He suddenly realized that the pattern of emission lines he was seeing matched the familiar Balmer series of hydrogen perfectly, but only if those lines had been redshifted by an enormous amount. The redshift of light is a phenomenon predicted by both the Doppler effect and, more importantly for cosmology, by the expansion of the universe itself. When an object moves away from us, the wavelengths of light it emits get stretched out, shifting toward the red end of the spectrum. The faster the object recedes, the greater the redshift. And in an expanding universe, the farther away an object is, the faster it appears to move away from us due to the expansion of space itself. Schmidt calculated that for 3C273, to show the redshift he was observing, it would have to be receding from us at roughly 16% of the speed of light. According to Hubble's law, which relates the speed of recession to distance, this meant 3C273 was approximately 2 billion light-years away. But here was the problem. If 3C273 was truly that far away, and yet still bright enough to be visible from Earth, it would have to be producing an absolutely staggering amount of energy, far more than any star possibly could. In fact, it would have to shine with the brilliance of trillions of stars combined. Schmidt published his findings in the journal Nature on March 16, 1963. The paper was less than a full page long, but its implications were profound. Schmidt had discovered the first quasar, though that term didn't exist yet. Within months, other astronomers had identified similar objects, and physicist Hong-Yi Chiu coined the term quasar, short for quasi-stellar radio source, in 1964. The name captured the paradoxical nature of these objects perfectly. They looked like stars, quasi-stellar, but they clearly weren't stars. They were something far more powerful and far more distant than anyone had imagined possible. Now, let's return to TON 618, still sitting in the Tonant-Zintla catalog, still masquerading as an ordinary blue star. In 1970, 13 years after its initial discovery, a radio survey being conducted in Bologna, Italy, detected radio emissions coming from the position of TON 618. This was a crucial clue. Ordinary stars don't typically emit strong radio waves. The detection of radio emission suggested that TON 618 might be one of these mysterious quasi-stellar radio sources that had captured the astronomical community's attention. Following up on the radio detection, astronomers obtained optical spectra of TON 618 to investigate further. What they found confirmed the suspicions raised by the radio detection. The spectrum of TON 618 showed emission lines characteristic of a quasar, and those lines were redshifted by an enormous amount. The redshift value was measured at 2.2119, which translates to looking back through time to when the universe was only about 3 billion years old. The light travel distance works out to approximately 10.8 billion light years. When we look at Taun 618 today, we're seeing light that left this object when our universe was less than a quarter of its current age. But the observations revealed something else, something that hinted at the extraordinary nature of the black hole powering this distant quasar. The emission lines in Taun 618's spectrum were extraordinarily wide, broader than those seen in most other quasars studied at the time. In spectroscopy, the width of an emission line tells you how fast the material emitting that light is moving. A wider line means the material is moving at a greater range of velocities, swirling around at tremendous speeds. The broad lines in Taun 618's spectrum indicated that gas near the black hole was moving at velocities exceeding 10,500 kilometers per second, more than 3% of the speed of light. This was measured directly from the hydrogen beta spectral line, providing clear indication of a very strong gravitational force at work. This gas was caught in the intense gravitational field of the black hole, orbiting in a chaotic disk before eventually spiraling inward to its doom. The faster this gas is moving, the stronger the gravitational field must be, and the stronger the gravitational field, the more massive the black hole at the center must be. The full-width, half-maxima measurements of Taun 618 turned out to be the largest among 29 quasars studied using this technique, with those hints of speeds reaching 10,500 kilometers per second, providing a direct window into the immense gravitational forces at play in this distant cosmic engine. For decades, Taun 618 was recognized as an exceptionally bright and distant quasar, but it wasn't until the 21st century that astronomers truly grasped the monster that lurked at its heart. As methods for estimating the masses of supermassive black holes improved through the 2000s and 2010s, astronomers used the width of those emission lines, combined with sophisticated models of how gas orbits around black holes, to calculate the mass of the object at Taun 618's heart. Different studies using different spectral lines and methods arrived at slightly different values, but they all pointed to the same stunning conclusion. One estimate, using the hydrogen beta line measurements, placed the mass at approximately 66 billion times the mass of our Sun. A more recent measurement in 2019, using the carbon-4 emission line as an alternative approach, found a somewhat lower velocity for the surrounding gas at about 2,761 kilometers per second, which indicated a mass closer to 40.7 billion solar masses. Regardless of which estimate is more accurate, the conclusion remains the same. Taun 618 harbors one of the most massive black holes ever discovered. To put this in perspective, that's more than 15,300 times the mass of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, which weighs in at a comparatively modest 4.15 million solar masses. Using the higher mass estimate, the black hole at Taun 618 contains more mass than all the stars in the Milky Way combined, which total approximately 64 billion solar masses spread across 100,000 light-years of space. Taun 618 had revealed itself to be not just a distant quasar, but home to what astronomers now classify as an ultramassive black hole, a cosmic monster that challenges our understanding of how such objects could have grown so large in the relatively short time since the Big Bang. Understanding scale, from familiar to unfathomable. To truly appreciate the enormity of TON 618 and the black hole at its center, we need to embark on a careful journey through cosmic scales, building our intuition step by step from the familiar to the incomprehensible. Let's start with something we can at least conceptually grasp: the speed of light. Light travels at approximately 300,000 kilometers per second, or, if you prefer, about 186,000 miles per second. This is the ultimate speed limit of the universe, the fastest that anything can possibly move through space. At this incredible velocity, light could circle Earth's equator more than 7 times in just 1 second. If you could somehow flip a light switch and watch the light travel, it would zip from New York to Los Angeles in about 16 thousandths of a second, faster than the blink of an eye. Despite this tremendous speed, light still takes time to cross the vast distances of space. It takes light about 1.3 seconds to travel from the Moon to Earth, which is why there was a delay in communications during the Apollo missions. It takes light about 8 minutes and 20 seconds to travel from the Sun to Earth, which means that when you look at the Sun during a sunrise or sunset, you're seeing it not as it is now, but as it was 8 minutes and 20 seconds ago. And it takes light about 4.24 years to reach us from Proxima Centauri, the nearest star to our solar system beyond the Sun. That distance, the distance light travels in 1 year, is what we call a light year. It's approximately 9.46 trillion kilometers, or about 5.88 trillion miles. This is the measuring stick astronomers use to discuss interstellar distances, because miles and kilometers become absurdly unwieldy when talking about the distances between stars. To give you a sense of just how far a light year is, if you could somehow travel at the speed of a commercial jet, about 900 kilometers per hour, it would take you more than 1.2 million years to cover the distance of a single light year. Our Milky Way galaxy, that grand spiral of stars and gas and dust that we call home, stretches approximately 100,000 light years from edge to edge. If you could somehow board a spacecraft capable of traveling at the speed of light and set off from one edge of the galaxy to the other, the journey would take 100,000 years. Think about that for a moment. All of recorded human history, from the first written records in ancient Mesopotamia to the present day, spans only about 5,000 years. You could experience all of human civilization 20 times over in the time it would take light to cross our galaxy. Civilizations could rise, flourish, and fall into dust. Species could evolve and go extinct. Continents could drift across the face of the Earth, all within the time it takes light to make that crossing. Our galaxy isn't alone in space. It's part of what astronomers call the local group, a collection of more than 50 galaxies bound together by their mutual gravity. The largest member of this cosmic neighborhood is the Andromeda Galaxy, sitting about 2.5 million light-years away from us. On a clear, dark night far from city lights, you can actually see Andromeda with your naked eye as a faint smudge of light. What you're seeing is the combined glow of approximately 1 trillion stars, so distant that their light has been traveling for 2.5 million years to reach your eyes. When that light began its journey, our human ancestors had only recently begun to walk upright and were just starting to use the first primitive stone tools. Now, let's talk about TON 618. This quasar sits approximately 10.8 billion light-years away from Earth, based on the light travel time. Due to the expansion of the universe, its current co-moving distance is even greater, estimated at about 18.2 billion light-years. But let's focus on the light travel distance, the time it took for the light we're seeing to reach us. That distance is so vast that it strains comprehension. The light we detect from TON 618 today left that object 10.8 billion years ago, when the universe itself was only about 3 billion years old. When that light began its journey toward Earth, our planet didn't exist yet. Our sun hadn't yet been born. The atoms that now make up your body were scattered across different parts of the galaxy, perhaps inside dying stars, or drifting in clouds of interstellar gas. The universe looked vastly different than it does today. Galaxies were closer together, colliding and merging more frequently. The rate of star formation was much higher. The cosmic web of matter was still coalescing into the large-scale structures we see today. And that light, those photons emitted by TON 618, has been traveling through space, crossing the expanding gulf between galaxies for longer than our planet has existed. But distance is just one aspect of TON 618's enormity. Let's talk about the black hole itself, about the sheer mass concentrated at the heart of this distant quasar. Using the most commonly cited estimate, the black hole at TON 618 contains approximately 66 billion times the mass of our Sun. Let's spend some time really understanding what this means. Our Sun is already incomprehensibly massive by everyday standards. It contains about 333,000 times the mass of Earth. You could fit about 1.3 million Earths inside the Sun's volume. If you took all the planets in our solar system, all the asteroids, all the comets, all the dust and gas, and combined their mass, you'd get about 1/400th of the Sun's mass. The Sun dominates our solar system so completely that it accounts for 99.86% of all the mass in the entire system. Yet the Sun is just one star among hundreds of billions in our galaxy, and it's not even a particularly large star by stellar standards. It's what astronomers classify as a yellow dwarf, a fairly average, middle-aged star that will shine for a total of about 10 billion years before exhausting its fuel. There are stars in our galaxy that dwarf the Sun, red supergiants like Betelgeuse that could swallow the orbits of Mercury, Venus, Earth, Mars, and even Jupiter, if placed where our Sun is now. Imagine taking not just our Sun, but 66 billion suns, and compressing all that mass down into a region smaller than our solar system. That's what exists at the heart of TON 618. To make this even more concrete, consider that the Milky Way galaxy contains approximately 200 billion to 400 billion stars. Let's split the difference and say 300 billion stars. The total mass of all those stars combined is estimated at about 64 billion solar masses. The black hole at TON 618, all by itself, using the higher mass estimate, contains more mass than all the stars in the entire Milky Way galaxy combined. Think about that for a moment. One single object, one black hole, matches or exceeds the combined mass of 100,000 light-years worth of stars, gas, and dust. It's as if you took our entire galaxy, that vast island universe containing hundreds of billions of suns, countless nebulae, massive clouds of gas and dust, and crushed it all down into a point so small and so dense that it warped spacetime around itself into a bottomless gravitational well from which not even light can escape. Compared to Sagittarius A star, the supermassive black hole at the center of our own Milky Way, TON 618 is 15,300 times more massive. Sagittarius A star, with its mass of about 4.15 million suns, already seemed incomprehensibly large when it was measured. It's surrounded by stars that orbit it at velocities exceeding 5,000 kilometers per second, moving so fast that they complete orbits in just a few years, despite traveling paths that extend thousands of times farther from the black hole than Earth is from the Sun. Yet TON 618 makes Sagittarius A star look like a lightweight. If you could somehow replace Sagittarius A star with TON 618, the gravitational effects would be catastrophic. Stars throughout the central region of the galaxy would be flung into new orbits, or captured and torn apart. And here's where things get even more mind-bending. This enormous mass isn't spread out over a vast region. It's concentrated within something called the event horizon, a spherical boundary that marks the point of no return around the black hole. The event horizon isn't a physical surface like the ground beneath your feet or the surface of a planet. It's more like an invisible line in space, a threshold beyond which the laws of physics as we experience them cease to apply in familiar ways. Once something crosses the event horizon, whether it's a particle of light or a massive star, it can never escape. It will inevitably fall inward toward the singularity at the black hole's center, that point where all our theories break down and space-time curvature becomes infinite. The size of the event horizon depends directly on the mass of the black hole. For a non-rotating black hole, the event horizon sits at what's called the Schwarzschild radius, named after Karl Schwarzschild, the German physicist who first solved Einstein's equations to describe the geometry around a massive point. The Schwarzschild radius is directly proportional to mass. Double the mass of the black hole, and you double the radius of the event horizon. For an object with the mass of our Sun, the Schwarzschild radius works out to about 3 kilometers. For the Earth, it's about 9 millimeters. For TON 618, using the 66 billion solar mass estimate, the Schwarzschild radius extends to about 1,300 astronomical units from the center. An astronomical unit, abbreviated AU, is the average distance from Earth to the Sun, about 150 million kilometers or 93 million miles. 1,300 astronomical units means the event horizon of TON 618 extends to about 1,300 times the Earth-Sun distance. The diameter of the event horizon, measuring from one side to the other through the center, is about 2,600 astronomical units, or approximately 390 billion kilometers, which is about 242 billion miles. To put this in more tangible terms, let's consider our solar system. Mercury, the closest planet to the Sun, orbits at about 0.4 astronomical units. Earth, as we've established, sits at 1 astronomical unit. Mars orbits at about 1.5 astronomical units. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Saturn's orbit takes it to about 9.5 astronomical units from the Sun. Uranus, the 7th planet, orbits at about 19 astronomical units. And Neptune, the outermost major planet in our solar system, orbits at about 30 astronomical units from the Sun. The event horizon of TON 618 extends more than 40 times farther than Neptune's orbit. If you placed the black hole where our Sun is, its event horizon would stretch far beyond the orbit of every planet, beyond the Kuiper belt where Pluto dwells at about 40 astronomical units, beyond the scattered disk extending to about 100 astronomical units, even beyond the heliopause where the Voyager spacecraft are now traveling at about 120 astronomical units. In fact, you'd need to go out to the inner edge of the Oort cloud. that theoretical shell of icy objects that begins around 2,000 astronomical units from the Sun, before you'd finally reach a distance comparable to Tone 618's event horizon. Some descriptions say you could fit 11 complete solar systems inside Tone 618's event horizon if you measure each solar system from the Sun out to Neptune's orbit. Imagine lining up 11 copies of our solar system, each one stretching 30 astronomical units from its central star, and placing them side by side across the diameter of this black hole's event horizon. That's the scale we're talking about. This is an object so large that our entire cosmic neighborhood, everything we've ever known directly, becomes a tiny subset of its domain. But wait, there's more to understand here. If you were somehow able to travel at the speed of light around the circumference of Taoyan 618's event horizon, tracing a circle around this cosmic giant, the journey would take you approximately 71 days and 14 hours. Think about that. Light, traveling at 186,000 miles every single second, would need more than 2 months to complete a lap around this black hole's point of no return. An astronaut could launch from Earth, orbit the planet dozens of times, return safely, and still have time to spare, all while light completed just one circuit around Taoyan 618's event horizon. The numbers become so large that they almost lose meaning in conventional terms. We're talking about an event horizon with a diameter of 195 billion kilometers. To put that in perspective, the diameter of Earth's orbit around the Sun, measuring from one side to the other, is about 300 million kilometers. Ton 618's event horizon is 650 times wider than Earth's entire orbit. It's so large that if you could somehow look at it from a distance with your naked eye, assuming it were close enough and bright enough to see, the event horizon would appear to have an angular size comparable to the full moon seen from Earth, but only if you were viewing it from about 20 light-years away. But Ton 618 isn't just massive and large. It's also extraordinarily bright, and that brightness is intimately connected to its mass and what's happening around it. The incredible luminosity, a cosmic lighthouse. The light we see from Ton 618 doesn't come from the black hole itself. This is a crucial point to understand. Black holes, by their very nature, don't emit light. The event horizon is the ultimate dark surface, a one-way membrane that allows nothing to escape, not even photons of light. If you could somehow hover just outside the event horizon and shine a flashlight straight outward, perpendicular to the surface, the light would escape, though it would be severely red-shifted and weakened by the intense gravitational field. But if you tilted that flashlight even slightly toward the horizon, angling the beam just a few degrees off perpendicular, the light would curve back and fall into the black hole, lost forever. The event horizon is the point where the escape velocity equals the speed of light, and since nothing can travel faster than light, nothing can escape once it crosses that boundary. So what makes Ton 618 so incredibly bright? What we're seeing when we observe this quasar is the death scream of matter falling into the black hole. The last burst of energy released before that matter crosses the point of no return and is lost forever to the universe outside. This process of matter falling into a black hole is called accretion, and it's one of the most efficient energy conversion processes in nature. When matter approaches a black hole, it doesn't typically fall straight in. Due to conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull in their arms, the matter forms a rotating disk around the black hole. This structure is called an accretion disk, and it's one of the most violent environments in the universe. Picture a flattened spiral of gas and dust, perhaps dotted with larger chunks of matter, all swirling around the black hole like water circling a drain. As material in the disk spirals inward, it rubs against neighboring material in adjacent orbits. This friction is incredibly powerful. The particles in the inner regions of the disk are orbiting at significant fractions of the speed of light, while particles slightly farther out are moving somewhat slower. This difference in orbital velocities creates shearing forces that heat the disk through friction. It's similar to how rubbing your hands together creates heat, but amplified to an almost unimaginable degree by the tremendous speeds and densities involved. The heat generated by this friction is extraordinary. The innermost regions of the accretion disk around a supermassive black hole like TOAN 618 can reach temperatures of millions of degrees. At these temperatures, the disk doesn't just glow red like heated metal or white like a star's surface. It radiates across the entire electromagnetic spectrum, from low-frequency radio waves through infrared, visible light, ultraviolet, X-rays, and even gamma rays at the highest energies. The disk becomes a multi-wavelength beacon, announcing its presence across the cosmos. The efficiency of this energy conversion is remarkable. When hydrogen fuses into helium in the core of a star like our Sun, the process converts about 0.7% of the hydrogen's mass into energy according to Einstein's famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. This is the process that powers the Sun and all ordinary stars, and it's impressively efficient compared to chemical reactions like burning coal or wood, which convert only a tiny fraction of matter's mass into energy. But accretion onto a black hole can convert 10% or even more of matter's mass directly into energy, making it more than 14 times more efficient than fusion. This means that for every kilogram of matter that falls into the accretion disk around TOAN 618, up to 100 grams of that mass, 10%, is converted into pure radiant energy before the matter crosses the event horizon. The rest falls into the black hole, adding to its mass, but that 10% converted to energy is what we see as the quasar's incredible brightness. The luminosity of TOAN 618, the total amount of energy it radiates per second across all wavelengths of light, has been measured at approximately 4 times 10 to the 40th power watts. Let's write that number out to get a sense of its magnitude. That's 40 million trillion watts. It's a number so large that it becomes almost meaningless in conventional terms. To make it more comprehensible, astronomers often express this luminosity in terms of solar luminosities, using the Sun's energy output as a measuring stick. Our Sun radiates about 3.8 times 10 to the 26th power watts, making it fairly typical for a star of its type. This energy output has remained relatively stable for the past 4.6 billion years, and it will continue at roughly the same level for another 5 billion years, until the Sun exhausts its hydrogen fuel. When you do the math and compare TOAN 618's luminosity to the Sun's, you find that TOAN 618 shines with the combined light of approximately 140 trillion suns. Let's pause and really contemplate that number. 140 trillion. If you took 140 trillion stars, just like our Sun, and added up all their light output, you'd get the brightness of TOAN 618. Now, consider that the Milky Way galaxy, our home galaxy, containing somewhere between 200 billion and 400 billion stars of all different types and sizes, has a total luminosity of perhaps 25 billion solar luminosities. That means TON 618, powered by a single supermassive black hole and its accretion disk, shines about 5,600 times brighter than an entire galaxy of hundreds of billions of stars. Think about the implications of this. Our entire galaxy, stretching 100,000 light-years across, filled with all its glowing nebulae and star clusters and spiral arms blazing with young blue stars and ancient red giants, all of that combined produces only about 1/5,000th the light of TON 618. You could take 5,600 copies of the Milky Way, place them all together, and their combined light output would equal what's coming from the region immediately around TON 618's black hole, a region vastly smaller than a single galaxy. To put this in even more visceral terms, imagine if you could somehow place TON 618 in our night sky, safely distant so that the radiation wouldn't harm us, but close enough to be visible. How bright would it appear? If you placed TON 618 at the same distance as the nearest star to our Sun, Proxima Centauri at 4.24 light-years away, TON 618 would shine trillions of times brighter than our Sun appears from Earth. It would be bright enough to read by at midnight, bright enough to cast shadows, bright enough to outshine the full moon by a factor of billions. The comparison breaks down because at that distance the radiation from TON 618 would actually sterilize Earth and probably vaporize the planet, but it gives you some sense of the absurd power output of this object. In fact, with an absolute magnitude of -30.7, TON 618 is one of the most luminous objects ever discovered in the universe. Absolute magnitude is the brightness an object would have if it were placed at a standard distance of 10 parsecs, about 32.6 light-years away. For comparison, the Sun has an absolute magnitude of about positive 4.8. The lower the number and the more negative it is, the brighter the object. A difference of 5 magnitudes corresponds to a brightness difference of exactly 100 times. TON 618's absolute magnitude is about 35.5 magnitudes brighter than the Sun, which translates to that factor of 140 trillion times we discussed earlier. This tremendous luminosity tells us something important about what's happening near the black hole. It tells us that matter is falling into TON 618 at a prodigious rate. To sustain this level of brightness, the accretion disk must be consuming matter at a rate equivalent to several solar masses per year. Some estimates suggest TON 618 might be accreting matter at a rate of roughly 1 solar mass every 2 days, which works out to about 183 solar masses per year. That's like dropping the equivalent of an entire star into the accretion disk every 2 days, and converting a significant fraction of its mass into pure energy. Where does all this matter come from? In the early universe, when TON 618's black hole was actively growing, the supply of gas was much more plentiful than it is in today's more mature cosmos. Galaxies were colliding and merging more frequently, funneling vast streams of gas toward their central regions. The cosmic web was still coalescing, with matter flowing along filaments and collecting in dense nodes. The black hole at TON 618's center would have been surrounded by an essentially limitless buffet of gas and dust, feeding voraciously and shining brilliantly as a result. But here's something fascinating to consider. As bright as TON 618 is, it might not even be feeding at the maximum possible rate. There's a theoretical limit to how quickly a black hole can accrete matter, called the Eddington limit, named after British astrophysicist Arthur Eddington. The Eddington limit arises from a balance between the inward pull of gravity and the outward push of radiation pressure. As matter falls toward a black hole and gets heated in the accretion disk, it radiates energy. This radiation exerts an outward pressure on the surrounding gas, pushing it away. If the black hole tries to eat too quickly, the radiation becomes so intense that it blows away the incoming matter, like trying to drink from a fire hose that's so powerful it pushes the water away from your mouth. The Eddington limit is the maximum rate at which a black hole can steadily accrete matter without the radiation pressure overwhelming the gravitational attraction. For a black hole with 66 billion solar masses, the Eddington luminosity, the maximum brightness it could sustain through steady accretion, works out to about 10 to the 41st power watts. TON 618's measured luminosity of 4 times 10 to the 40th power watts is actually below the Eddington limit, suggesting it's feeding at a relatively sustainable rate rather than in some extreme super Eddington outburst. This is both reassuring and somewhat puzzling. It's reassuring because it means the physics we understand can explain TON 618's brightness without invoking exotic processes. It's puzzling because if TON 618 has been feeding at or below the Eddington limit for most of its life, how did it manage to grow so massive in just 3 billion years? The brightness of TON 618 has another important consequence. This incredible output of energy affects the surrounding gas on galactic scales. As the radiation streams outward from the accretion disk, it heats and ionizes gas throughout the host galaxy and beyond. Astronomers have detected what's called a lyman-alpha nebula surrounding TON 618, a vast cloud of glowing hydrogen gas that's been excited by the quasars' intense radiation. This nebula is enormous, with a diameter of at least 100 kiloparsecs, which is about 330,000 light-years across. To put that in perspective, that's more than twice the diameter of the Milky Way galaxy. The nebula actually consists of 2 main components: an intermolecular outflow of gas being pushed outward by the energy from the quasar, and an extensive outer region of cold molecular gas in what's called the circumgalactic medium, the diffuse halo of gas surrounding the galaxy. Each of these components has an estimated mass of 50 billion solar masses, comparable to the mass of the central black hole itself. Both regions are aligned with the radio jets produced by the central quasar, suggesting that the black hole's activity is fundamentally shaping the distribution of gas across the entire system. The extreme radiation from TON 618 excites the hydrogen in this nebula so intensely that it glows brightly in a specific ultraviolet wavelength called the lyman-alpha line, an emission line produced when electrons in hydrogen atoms drop from the second energy level down to the first, releasing a photon with a wavelength of about 121 nanometers. This is normally an ultraviolet wavelength invisible to our eyes and absorbed by Earth's atmosphere, but because TON 618 is so distant and its light is so redshifted, this ultraviolet emission has been shifted into the visible part of the spectrum by the time it reaches us, allowing ground-based telescopes to observe it. These lyman-alpha blobs, or LABs as astronomers call them, are thought to be precursors of modern-day galaxies, systems where intense central activity from a quasar is driving the evolution of the surrounding galaxy. By studying TON 618 and its enormous lyman-alpha nebula, astronomers gain insight into the processes that drove galaxy evolution in the early universe, particularly how quasars ionized their surroundings and influenced star formation across vast regions of space. Due to the brilliance of the central quasar, the surrounding host galaxy itself is completely outshone, and hence is not visible from Earth in direct observations. The quasar is so bright that it's like trying to see a candle flame next to a searchlight. The light from billions of stars in the host galaxy is simply overwhelmed by the blaze from the accretion disk. Astronomers know the host galaxy must be there, because the black hole had to form somehow, and black holes don't exist in isolation. But actually, observing the galaxy's stellar population requires sophisticated techniques to subtract or block the quasar's light, similar to how a coronagraph blocks the sun's glare to reveal its fainter corona. This incredible brightness makes TON 618 visible across more than 10 billion light-years of space, allowing us to study in detail an object from when the universe was a quarter of its current age. Without this extraordinary luminosity, TON 618 would be invisible to us, lost in the depths of space and time. But because it shines so brilliantly, it serves as a beacon, a cosmic lighthouse that illuminates conditions in the early universe and allows us to probe questions about how massive black holes formed and evolved in those primordial times, the nature of quasars and supermassive black holes. To understand what makes TON 618 so remarkable, we need to delve deeper into the nature of quasars and the supermassive black holes that power them. What exactly is a black hole at its most fundamental level, and how does one become so massive? What is this accretion disk that produces such tremendous energy? Let's explore these questions carefully, building up a picture of these exotic objects piece by piece. A black hole, at its most fundamental level, is a region of spacetime where gravity has become so strong that not even light can escape. This concept emerges directly from Einstein's general theory of relativity, published in 1915. Einstein showed that what we experience as gravity isn't really a force pulling objects together in the traditional sense, but rather a curvature of spacetime itself, caused by the presence of mass and energy. Massive objects warp the fabric of spacetime around them, creating depressions or wells in the cosmic fabric, and other objects moving through that warped spacetime follow curved paths that we interpret as gravitational attraction. Imagine spacetime as a flexible rubber sheet stretched out flat. If you place a heavy ball on this sheet, it creates a depression, a curved region around the ball. Now, if you roll a marble across the sheet near the marble will curve toward the ball, following the contours of the depression. This is analogous to how planets orbit stars, and how light bends as it passes near massive objects. The more massive the object, the deeper and steeper the depression it creates. When enough mass becomes concentrated in a small enough region, the warping of spacetime becomes extreme. There comes a point where the curvature is so severe that it creates a one-way surface in spacetime, a boundary called the event horizon. Anything that crosses this boundary, whether a particle of matter, a photon of light, or even information itself, will find all possible future paths leading inward toward the center. There's no escape, no clever trajectory that could carry you back out across that boundary. Crossing the event horizon is like falling into the future. Once you've gone past it, reaching the singularity at the center becomes as inevitable and unavoidable as tomorrow following today. The size of the event horizon depends on the mass of the black hole. For a non-rotating black hole, the event horizon sits at what's called the Schwarzschild radius, named after Karl Schwarzschild, the German physicist and astronomer who, remarkably, solved Einstein's field equations to describe the geometry around a spherically symmetric mass while serving in the German army during World War I. Schwarzschild completed this groundbreaking work in the trenches, calculating the precise mathematical description of what we now call a black hole, even though the term wouldn't be coined for another 50 years. Tragically, Schwarzschild died just a few months after completing this work, never knowing the profound impact his solution would have on our understanding of the universe. The Schwarzschild radius is directly proportional to mass. If you double the mass of the black hole, you double the radius of the event horizon. The formula is surprisingly simple. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For an object with the mass of our Sun, the Schwarzschild radius works out to about 3 kilometers. For the Earth, it's about 9 millimeters, smaller than a grape. For Ton 618's 66 billion solar mass black hole, the Schwarzschild radius extends to about 1,300 astronomical units from the center, as we discussed earlier. Of course, neither the Sun nor the Earth are actually black holes, because their matter isn't compressed to fit within their respective Schwarzschild radii. The Sun's actual radius is about 700,000 kilometers, far larger than the 3-kilometer Schwarzschild radius it would need to collapse within to become a black hole. Earth's radius is about 6,400 kilometers, vastly bigger than that 9-millimeter Schwarzschild radius. For these objects to become black holes, you'd have to compress all their mass into regions smaller than those critical radii, which would require forces far stronger than any we encounter in everyday physics or even in most cosmic environments. But in the extreme conditions found in the cores of massive stars at the ends of their lives, such compression can occur. When a star more than about 20 to 25 times the mass of the Sun exhausts its nuclear fuel, there's no longer enough outward pressure from fusion reactions to support the star against its own gravity. The core collapses catastrophically in a matter of seconds. If conditions are right, and the core is massive enough, the collapse doesn't stop when neutrons touch. It continues past even that extraordinary density, compressing the core until all its mass has been squeezed into a region smaller than its Schwarzschild radius. A stellar mass black hole is born, typically containing anywhere from 3 to perhaps 100 solar masses depending on the progenitor star. But Ton 618's black hole isn't a stellar mass black hole formed from a single collapsing star. It's a supermassive black hole, containing not just dozens or hundreds, but tens of billions of times the Sun's mass. How do such monsters form and grow? The honest answer is that we're not entirely sure. The formation and growth of supermassive black holes, particularly the ultramassive ones like Ton 618, remains one of the major unsolved problems in astrophysics, a puzzle that keeps theorists up at night and drives observational campaigns to peer ever deeper into the early universe. One possibility is that supermassive black holes grow from stellar mass seeds through a gradual process of accumulation. A stellar mass black hole forms from a massive star's collapse. Over time, it accretes gas from its surroundings, growing slowly but steadily. Occasionally, it might merge with another black hole when two massive stars in a binary system both end their lives as black holes and eventually spiral together. Through this process of feeding and merging repeated over billions of years, perhaps a stellar mass black hole of 10 solar masses could eventually grow to 1 million, then 10 million, then 100 million, and finally billions of solar masses. But there's a problem with this scenario, particularly for black holes like Tone 618 that exist when the universe was only 3 billion years old. Growing a black hole takes time. If a black hole feeds at the maximum sustainable rate, accreting matter at the Eddington limit we discussed earlier, its mass grows exponentially with a characteristic time scale called the salpeter time, which is about 45 million years, starting from a 10 solar mass seed and growing continuously at the Eddington limit. You could in principle grow to 1 billion solar masses in about 1 billion years. But Ton 618's black hole contains 66 billion solar masses and exists when the universe was only 3 billion years old. Even if we assume the black hole started forming almost immediately after the Big Bang and grew at the maximum rate every single moment since then, it's challenging to explain how it reached such an enormous mass so quickly. And we have good reason to think black holes didn't start forming immediately. The first stars probably didn't form until the universe was about 100 to 200 million years old, as the initial hydrogen and helium gas cooled and collected into the first protogalaxies. So, Ton 618's black hole had perhaps only 2.8 billion years to grow from its initial seed to 66 billion solar masses, which makes the growth rate problem even more severe. This has led astronomers to consider alternative formation scenarios. Perhaps some supermassive black holes didn't form from stellar mass seeds at all. Perhaps they began as much more massive objects right from the start. In the early universe, conditions were very different from today. Gas was denser, and there were no heavy elements yet. No carbon or oxygen or iron. Only hydrogen and helium forged in the Big Bang. In this pristine environment, theory suggests that massive gas clouds, containing perhaps 10,000 to 1 million solar masses, might have collapsed directly into black holes without ever forming stars. These direct collapse black holes would provide a much larger starting seed, cutting hundreds of millions of years off the growth time needed to reach supermassive proportions. Starting from a seed of 100,000 solar masses instead of 10 solar masses makes the problem of growing to 66 billion solar masses much more tractable, though still challenging. Another possibility involves what are called supermassive stars, hypothetical objects that might have formed in the very early universe, containing hundreds or thousands of solar masses. These objects would be unstable and short-lived, quickly collapsing into black holes that again would provide much larger seeds than ordinary stellar collapse. There's also the possibility that growth sometimes exceeds the Eddington limit. While steady accretion at super Eddington rates is difficult because the radiation pressure pushes away incoming material, perhaps under certain conditions like major galaxy mergers, black holes experience brief episodes of extremely rapid super Eddington accretion that allow them to bulk up quickly. Or perhaps multiple smaller black holes merge together during the chaotic early phases of galaxy formation, combining their masses into a single ultramassive object. The truth is probably some combination of these mechanisms. Different supermassive black holes might have formed and grown through different pathways. Ton 618's existence as a 66 billion solar mass black hole just 3 billion years after the Big Bang serves as a crucial observational constraint on our theories, challenging us to explain not just how black holes can grow, but how they can grow so large so quickly in the cosmic timescale. Now, let's turn to the process that makes these black holes visible across billions of light years. Accretion. When matter approaches a black hole, it doesn't typically fall straight in along a radial path. Due to conservation of angular momentum, that fundamental principle of physics that keeps spinning ice skaters spinning and planets orbiting. The matter forms a rotating disk around the black hole. Picture a flattened spiral of gas and dust, perhaps dotted with larger chunks of matter from disrupted stars or molecular clouds, all swirling around the black hole like water spiraling toward a drain. This structure is called an accretion disk, and understanding its physics has been one of the great triumphs of theoretical astrophysics over the past 50 years. As material in the disk spirals inward, it moves in approximately circular orbits, but each orbit is slightly smaller and faster than the one before. This creates shearing between adjacent regions, like layers in a deck of cards sliding past each other. The friction produced by this shearing motion is incredibly powerful, far stronger than any friction we experience in everyday life. Think about what happens when you rub your hands together quickly. The friction between your palms converts some of the kinetic energy of the motion into heat, warming your hands. The same basic principle applies in the accretion disk, but amplified to an almost unimaginable degree. The particles in the inner regions of the disk are orbiting at significant fractions of the speed of light, perhaps 30% or 40% of light speed for the innermost stable orbits around a supermassive black hole. Material slightly farther out is moving somewhat slower. This difference in orbital velocities creates shearing forces that heat the disk through viscous dissipation, the conversion of ordered motion into random thermal motion, which we experience as heat. The heat generated is extraordinary. The innermost regions of the accretion disk around a supermassive black hole like TON 618 can reach temperatures of millions or even tens of millions of degrees Kelvin. At these temperatures, matter doesn't exist in any form familiar from everyday experience. The atoms are completely ionized, stripped of their electrons by violent collisions, creating a plasma of free electrons and atomic nuclei. This plasma doesn't just glow red like heated metal or white like a star's surface. It radiates across the entire electromagnetic spectrum, from low-frequency radio waves through infrared, visible light, ultraviolet, and into the X-ray and even gamma-ray portions of the spectrum. Different regions of the disk emit different types of radiation based on their temperature. The cool outer regions, perhaps a few thousand degrees, emit mainly in the infrared. Mid-disk regions at temperatures of tens of thousands of degrees emit optical and ultraviolet light. The inner disk, at millions of degrees, blazes in X-rays. This is why quasars are called broadband emitters. They shine across the entire spectrum, making them visible to radio telescopes, infrared telescopes, optical telescopes, and X-ray observatories alike. The efficiency of this energy conversion process is remarkable and worth dwelling on for a moment. When hydrogen fuses into helium in the core of a star like our Sun, about 0.7% of the hydrogen's mass is converted into energy, according to Einstein's equation E equals mc squared. This is the process that has powered the Sun for 4.6 billion years, and will continue to power it for another 5 billion years or so. Nuclear fusion is impressively efficient compared to chemical reactions like burning coal or wood, which convert only a tiny fraction, perhaps a billionth or less, of matter's mass into energy. But accretion onto a black hole can convert anywhere from about 6% to over 40% of matter's mass directly into energy before the matter crosses the event horizon and is lost forever. The exact efficiency depends on the black hole's spin and the geometry of the accretion flow. A non-rotating black hole can convert about 6% of accreting matter's mass to energy. A rapidly spinning black hole, with the disk orbiting in the same direction as the black hole's spin, can achieve efficiencies exceeding 40% due to frame dragging effects in the ergosphere, the region just outside the event horizon, where spacetime itself is forced to rotate with the black hole. Think about what this means. For every kilogram of matter that falls toward TON 618's black hole and swirls through the accretion disk, somewhere between 60 grams and 400 grams of that mass is converted into pure radiant energy before crossing the point of no return. The rest adds to the black hole's mass, making it even more massive and increasing its gravitational pull. This incredible efficiency, more than 8 times better than fusion in the most optimistic case, is why quasars can shine so brilliantly. They're tapping into the fundamental equivalence between mass and energy at a rate that no other natural process in the universe can match. The structure of the accretion disk itself is complex and varies depending on the rate at which matter is flowing inward. When the accretion rate is relatively low, the disk can be geometrically thin, meaning its vertical thickness is small compared to its radial extent. These thin disks, described by the Shakura-Sunyaev model developed in the 1970s, are relatively cool and radiate their energy efficiently. They're sometimes called standard disks because this configuration applies to many observed systems. But when the accretion rate is very high, approaching or exceeding the Eddington limit, the disk becomes thick and puffy. The intense radiation pressure from within the disk tries to push material outward, causing the disk to inflate. These thick disks, sometimes called slim disks, or in the extreme case advection-dominated accretion flows, can be geometrically thick, with a vertical scale height comparable to the radial distance from the black hole. They're less efficient at radiating energy, and some of the heat gets trapped and falls into the black hole along with the matter, a process called advection that gives these flows their name. For TON 618, shining at a luminosity of 4 times 10 to the 40th power watts, the accretion rate is likely quite high but probably still below the super Eddington regime. The disk is efficiently converting the gravitational potential energy of in-falling matter into radiation that streams outward across the cosmos, creating the brilliant beacon we observe from 10 billion light-years away. The physics of extreme gravity. Space-time near the event horizon. Now, let's explore what happens to space-time itself near a black hole as massive as TON 618, and what bizarre effects emerge when gravity becomes so strong that it warps the very fabric of the universe. Near the event horizon of TON 618, the curvature of spacetime reaches levels that defy everyday intuition, creating effects that seem more like science fiction than science fact. Yet they're all predicted by Einstein's general relativity, and, where we've been able to test them, confirmed by observation. Let's start with time dilation, perhaps the most mind-bending consequence of extreme gravity. According to general relativity, time flows more slowly in stronger gravitational fields. This isn't an illusion or a measurement artifact. Time itself, the progression from past to future, actually runs at different rates depending on the strength of the gravitational field. We've measured this effect right here on Earth. Atomic. Clocks at sea level, experiencing slightly stronger gravity than identical clocks on mountaintops, actually tick slower by a measurable amount. GPS satellites have to account for time dilation effects, or their positioning calculations would be off by kilometers. Near a massive black hole like TON 618, time dilation becomes extreme. Imagine you had a friend who volunteered for a dangerous experiment. They agree to approach TON 618's event horizon in a specially equipped spacecraft while you remain at a safe distance far from the black hole, watching through a powerful telescope. As your friend approaches the event horizon, you would notice something strange. Their clock, visible through your telescope, would appear to tick more and more slowly. Their movements would seem to slow down, as if they were moving through thick syrup. Your friend, however, would notice nothing unusual about their own clock or movements. From their perspective, time would flow normally. They would see your clock far from the black hole, ticking faster and faster as they descended. This isn't a matter of light travel time or relativistic speeds. It's a fundamental feature of space-time itself. Time genuinely flows at different rates in different gravitational fields. As your friend approached within a few Schwarzschild radii of the event horizon, the time dilation would become dramatic. 1 hour on their clock might correspond to days, then weeks, then years on your distant clock. At the event horizon itself, the time dilation becomes infinite from your perspective. You would see your friend slow down more and more as they approached the horizon, their image becoming increasingly redshifted and dim, but you would never actually see them cross it. They would appear frozen at the event horizon, their last moment before crossing stretched out to eternity from your reference frame. But from your friend's perspective, something completely different happens. They would reach the event horizon in a finite amount of their own time, perhaps just a few hours depending on their trajectory. They would cross it without noticing anything particularly special at that exact moment. There's no wall at the event horizon, no barrier they would impact. The event horizon is simply a mathematical surface, a point of no return. Once crossed, however, their fate would be sealed. All their possible future paths would lead inward toward the singularity at the center. Inside the event horizon, the roles of space and time become weirdly interchanged in a sense. Reaching the singularity becomes as inevitable as the future. Just as you, outside a black hole, cannot avoid moving forward in time no matter what you do, someone inside the event horizon cannot avoid moving toward the singularity. It's not a matter of acceleration or thrust or cleverness. The singularity is simply in your future once you've crossed the horizon, as unavoidable as tomorrow. Now, let's talk about what's called the photon sphere, an imaginary surface that exists outside the event horizon at exactly 1.5 times the Schwarzschild radius for a non-rotating black hole. At this distance, space-time is curved so severely that light can actually orbit the black hole. Photons, massless particles of light that always travel at exactly the speed of light in any reference frame, can enter circular orbits around the black hole at this special radius. For TON 618, with an event horizon at 1,300 astronomical units, the photon sphere would sit at about 1,950 astronomical units from the center. This is an unstable orbit, meaning that any slight perturbation would cause a photon to either spiral inward and fall into the black hole or escape outward to infinity. But theoretically, if you could place yourself exactly at the photon sphere and look around, you might see the back of your own head. Light leaving the back of your head would travel all the way around the black hole and return to your eyes. Of course, this is purely theoretical. The intense radiation near a quasar like TON 618 would vaporize any matter long before reaching the photon sphere. but it's a fascinating consequence of curved spacetime nonetheless. Inside the photon sphere but outside the event horizon lies another important radius called the innermost stable circular orbit, or ISCO. This is the smallest radius at which matter can orbit the black hole in a stable circular path. For a non-rotating black hole, the ISCO sits at 3 times the Schwarzschild radius, 3,900 astronomical units from Ton 601's center. Inside this radius, there are no stable circular orbits. Matter at the ISCO is already traveling at about half the speed of light, orbiting this cosmic giant approximately once every few months of its own time, though from a distant observer's perspective, the orbital period would appear longer due to time dilation. If the black hole is spinning, which Ton 618 almost certainly is, the ISCO moves closer to the event horizon. For a black hole spinning at maximum possible rate, with the matter orbiting in the same direction as the spin, the ISCO can be as close as 1 Schwarzschild radius, right on top of the event horizon. This is why the spin of the black hole affects the accretion efficiency. Matter at a closer ISCO has more gravitational potential energy to release before crossing the event horizon, allowing higher conversion of mass to energy. The spinning of a massive black hole creates another remarkable effect called frame dragging, or the Lense-Thirring effect. A spinning black hole drags the surrounding spacetime around with it, like a spoon stirring honey. Near the event horizon, this frame dragging becomes so strong that nothing can remain stationary with respect to a distant observer. Everything, including light, is forced to co-rotate with the black hole's spin. The region where this occurs is called the ergosphere, and it exists between the event horizon and a surface called the static limit. In the ergosphere, remarkable things become possible. A process called the Penrose process, proposed by mathematical physicist Roger Penrose in 1969, allows energy to be extracted from a rotating black hole through particle interactions in the ergosphere. A particle entering the ergosphere can split into 2 particles, with one falling into the black hole and carrying negative energy from the black hole's perspective, while the other escapes with more energy than the original particle had. The black hole loses rotational energy in this process, but the escaping particle carries away more energy than went in. This could, in principle, power extremely energetic phenomena, possibly including the jets of particles that quasars sometimes produce perpendicular to their accretion disks. For Ton 618, if it's spinning at even a modest rate, the ergosphere would extend a considerable distance beyond the event horizon. In this region, the swirling spacetime might contribute to the organization of the accretion disk and the formation of any jets that might be present. The magnetic fields threading through the disk could be twisted and amplified by the frame dragging effect, potentially channeling matter and energy into narrow beams that blast out perpendicular to the disk at nearly the speed of light. Near the event horizon, the tidal forces become relevant. Tidal forces arise because gravity weakens with distance, so different parts of an extended object experience different gravitational pulls. On Earth, tidal forces from the Moon raise ocean tides, pulling water on the near side toward the Moon and on the far side away from Earth's center. Near a black hole, tidal forces become extreme. For a stellar mass black hole, perhaps 10 solar masses, the tidal forces at the event horizon would be strong enough to rip apart any solid object, a process astronomers call spaghettification because an unfortunate astronaut would be stretched lengthwise like spaghetti while being compressed from the sides. But interestingly, For a supermassive black hole like TON 618, the tidal forces at the event horizon are actually quite mild. The event horizon is so far from the central singularity that the difference in gravitational pull between your head and your feet, if you fell in feet first, would be relatively small at the moment you cross the horizon. You could cross the event horizon of TON 618 without being torn apart. You wouldn't feel anything particularly unusual at that exact moment. The spaghettification would come later, as you fell deeper into the black hole and approached the singularity, where space-time curvature becomes infinite, and all our theories break down. But at the horizon itself, for such a massive black hole, conditions would be surprisingly gentle. This is one of the paradoxes of black hole physics. The more massive the black hole, the larger the event horizon, and the more gentle the tidal forces at the horizon itself. TON 618's enormous mass makes its event horizon relatively safe to cross, at least initially, though your ultimate fate would still be the same. You would inevitably reach the singularity and be destroyed. Inside the black hole, beyond the event horizon where no information can ever escape, the nature of space-time becomes profoundly strange. Our mathematical models predict that space-time inside the event horizon has the singularity in all future directions. The singularity isn't a place at the center that you move toward spatially. It's more like a moment in time that exists in your inevitable future. Some solutions to Einstein's equations suggest even stranger possibilities inside rotating black holes. Ring singularities, wormholes to other universes, regions where time becomes space-like and space becomes time-like. But we have no way to test these predictions because no information from inside the event horizon can ever reach us. This brings us to one of the deep mysteries of black hole physics, the information paradox. According to quantum mechanics, information cannot be destroyed. The universe must always remember its complete quantum state. But black holes seem to violate this principle. Matter falling into a black hole carries information about its quantum state. But once it crosses the event horizon, that information seems to be lost to the outside universe. When Stephen Hawking showed in the 1970s that black holes slowly evaporate through what's now called Hawking radiation, a quantum effect near the event horizon, it seemed to make the problem worse. The black hole could eventually evaporate completely, and the information about everything that fell in would seem to vanish entirely from the universe. This paradox has driven decades of theoretical work at the intersection of quantum mechanics and general relativity. Recent developments suggest that information might be encoded in subtle correlations in the Hawking radiation, or in structures at the event horizon that we're only beginning to understand. But the complete resolution remains elusive, pointing to deep gaps in our understanding of how quantum mechanics and gravity work together at the most fundamental level. For TON 618, the Hawking radiation would be extraordinarily weak, with a temperature inversely proportional to its mass. While a stellar mass black hole might have a Hawking temperature of a few billionths of a degree above absolute zero, TON 618's temperature would be trillions of times smaller still, far colder than the cosmic microwave background radiation filling space. At this temperature, TON 618 absorbs far more energy from the cosmic background than it emits through Hawking radiation, so it's actually growing slightly from this quantum effect rather than shrinking. It would take an incomprehensibly long time, far longer than the current age of the universe by countless orders of magnitude, for TON 618 to evaporate through Hawking radiation. TON 618. In Cosmic Context, the Early Universe and Galaxy Formation. To truly appreciate the significance of TON 618, we need to understand its place in the broader cosmic story. When we observe TON 618, we're not just seeing a remarkably massive black hole. We're seeing a window into the early universe, into conditions that existed when the cosmos was young and wild, when galaxies were still forming, and the first generation of supermassive black holes were just reaching their peak power. TON 618 exists at a redshift of 2.219, which corresponds to a time when the universe was approximately 3 billion years old, about 22% of its current age of 13.8 billion years. This epoch, spanning from about 2 to 4 billion years after the Big Bang, is sometimes called cosmic noon by astronomers, and it represents a crucial period in cosmic history. Cosmic noon was the peak era of star formation in the universe. More stars were being born during this period than at any other time before or since. The universe was a much more active, violent place than it is today. At cosmic noon, galaxies were colliding and merging more frequently because they were closer together on average than galaxies are today. The expanding universe has stretched the distance between galaxy clusters over time. But 3 billion years after the Big Bang, the cosmos was more compact and crowded. These frequent galaxy mergers funneled enormous streams of gas toward galactic centers, feeding the supermassive black holes that lurked there. This is why quasars were much more common at cosmic noon than they are in the present-day universe. Nearly every massive galaxy probably went through a quasar phase at some point during its history, shining brilliantly as its central black hole gorged on a feast of infalling gas. TON 618 is one of the brightest beacons from this era, a quasar at the peak of its power. The galaxy hosting TON 618, though completely outshone by the quasar and, therefore invisible in direct observations, is likely undergoing intense star formation, possibly forming new stars at a rate hundreds of times faster than the Milky Way does today. The quasar itself, with its intense radiation and possible jets, is influencing star formation across the entire galaxy, an effect astronomers call feedback. Feedback from quasars plays a crucial role in regulating galaxy growth. The radiation and winds from an actively feeding supermassive black hole can heat gas throughout the galaxy, preventing it from cooling and condensing to form new stars. In the most extreme cases, quasar winds can actually blow gas out of the galaxy entirely, quenching star formation and potentially determining the final mass of the galaxy. There's a remarkably tight correlation between the mass of a galaxy's central supermassive black hole and the mass of stars in the galaxy's bulge, suggesting that black holes and their host galaxies co-evolve through some kind of feedback mechanism that we're still working to understand fully. For TON 618, the Lyman-alpha nebula we mentioned earlier, that vast cloud of glowing hydrogen surrounding the quasar, provides direct evidence of this feedback in action. The nebula contains about 100 billion solar masses of gas, comparable to the mass of the black hole itself, and representing a significant fraction of the galaxy's total matter. This gas is being heated and ionized by the quasar's radiation, and some of it is being pushed outward by radiation pressure and possibly by jets. This outflowing gas might eventually escape the galaxy entirely, carrying away matter that could otherwise form new stars or feed the black hole further. The fact that TON 618 exists at all when the universe was only 3 billion years old tells us something profound about the timeline of cosmic structure formation. Supermassive black holes had to form and grow to enormous sizes remarkably quickly in cosmic terms. This rapid growth requires either very massive seeds, as we discussed earlier, or sustained feeding at high rates, or both. The existence of TON 618 and similar ultramassive quasars in the early universe has driven much of the theoretical work on black hole formation scenarios over the past few decades. TON 618's place in cosmic history also makes it a powerful tool for studying the distribution of matter in the universe at that epoch. The light from TON 618, traveling for 10.8 billion years to reach us, passed through countless clouds of gas and countless gravitational fields on its journey. Each interaction left subtle imprints on the light, absorbing specific wavelengths or shifting frequencies through gravitational lensing. By carefully analyzing the spectrum of TON 618, astronomers can study not just the quasar itself, but the properties of all the material between us and the quasar, mapping the cosmic web and studying how matter was distributed when the universe was young. The fact that we can see TON 618 at all across such an enormous distance is testament to the universe's transparency to light. Between us and TON 618 lies approximately 10.8 billion light-years of space, but that space is remarkably empty. The density of matter in the intergalactic medium, the diffuse gas between galaxies, is extraordinarily low, perhaps 1 atom per cubic meter on average. This means light can travel for billions of years through the universe with relatively little absorption or scattering. The universe is, in a very real sense, transparent across most of its volume, allowing us to observe objects from its earliest epochs. However, the light from TON 618 has been profoundly affected by its journey through expanding space. The redshift of 2.219 means that all the wavelengths of light we receive from TON 618 have been stretched to 3.219 times their original wavelengths. Ultraviolet light emitted by the quasar has been stretched into the visible spectrum. Visible light has been shifted into the near-infrared. This redshift is caused by the expansion of space itself. As the light traveled toward us, the fabric of space through which it moved was continuously stretching, carrying the photons along and elongating their wavelengths in the process. This expansion of space, discovered by Edwin Hubble in the 1920s, is one of the fundamental features of our universe. It tells us that the universe had a beginning, the Big Bang, when all of space was compressed to a point and began expanding. It tells us that the universe is not static but dynamic, constantly changing and evolving. The light from distant quasars like TON 618, carrying information across billions of years, allows us to map this expansion history and study how the universe has evolved. Comparing cosmic giants, TON 618 and other massive black holes. TON 618 has long been recognized as one of the most massive black holes ever discovered, but it's valuable to place it in context by comparing it to other extreme objects we've found across the cosmos. This comparison not only helps us appreciate TON 618's extraordinary nature, but also reveals patterns about how supermassive black holes grow and what limits might exist on their maximum size. For many years, TON 618 held the record for the largest confirmed black hole by mass. However, recent discoveries have identified other contenders and raised questions about theoretical limits to black hole growth. Phoenix A, the central black hole in the Phoenix cluster located about 8.5 billion light-years away, is estimated to have a mass of approximately 100 billion solar masses, potentially making it even more massive than TON 618. Phoenix A sits at the center of the Phoenix cluster, one of the most massive and luminous galaxy clusters ever discovered, surrounded by tremendous amounts of hot gas and displaying evidence of extreme accretion activity. The Phoenix cluster's central black hole is estimated to be consuming matter at an astonishing rate, possibly up to 60 solar masses per year, though this is just the current rate and might vary significantly over time. The black hole's Schwarzschild diameter is approximately 3,900 astronomical units, and its event horizon is so large that a beam of light would take about 71 days to circumnavigate it. This makes Phoenix A potentially the largest known black hole in terms of both mass and physical size, though uncertainties in mass measurements mean the exact ranking between Phoenix A and DUN 618 remains somewhat ambiguous. What's particularly interesting about Phoenix A is that it may push up against theoretical limits for black hole growth. Physicist Andrew King at the University of Leicester calculated in Heinz 2015 that there should be a natural upper limit to black hole mass around 50 billion solar masses for non-spinning black holes, potentially extending to 270 billion solar masses for rapidly spinning black holes. This limit arises from a quirk in the physics of accretion. As a black hole grows more massive, its innermost stable circular orbit moves farther from the event horizon in absolute distance, even though it remains at the same radius measured in Schwarzschild radii. Eventually, the ESCO can be pushed beyond what's called the self-gravitational radius, the point where in-falling streams of gas become gravitationally bound to themselves rather than to the black hole. Once this happens, the gas can fragment into clumps and even form stars before reaching the black hole, dramatically reducing the accretion efficiency and slowing or stopping the black hole's growth. Phoenix A, with its estimated 100 billion solar mass, sits right at or slightly above King's upper limit for a non-spinning black hole, suggesting it might be spinning rapidly or that the theoretical limit needs refinement. TON 618, with 66 billion solar masses, also approaches this theoretical boundary. The existence of these ultramassive black holes suggests we're observing objects near the maximum possible size that black holes can achieve through steady accretion. Another notable comparison is with the black hole at the center of the galaxy IC 1101, a supergiant elliptical galaxy that was long cited as containing one of the most massive black holes. IC 1101 lies about 1 billion light-years away, and its central black hole was estimated at around 40 billion solar masses, though more recent measurements suggest it might be somewhat smaller. IC 1101 itself is an enormous galaxy, perhaps 4 to 6 times wider than the Milky Way in its stellar component, and it contains approximately 100 trillion stars. Closer to home, our own galaxy's central black hole, Sagittarius A star, provides an interesting point of comparison. At 4.15 million solar masses, it's absolutely dwarfed by TON 618, smaller by a factor of more than 15,000. Yet Sagittarius A star has been crucial to our understanding of black hole physics because its relative proximity, about 26,000 light-years away, allows us to observe it in unprecedented detail. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, capturing M87 star, the black hole at the center of galaxy Messier 87. In 2022, they released an image of Sagittarius A star itself, showing the glowing ring of emission from the accretion disk surrounding our galaxy's central black hole. M87 star weighs in at about 6.5 billion solar masses, about 10 times less massive than Toan 618, but still extraordinarily large. What makes M87 star particularly notable is its powerful jet, a narrow beam of matter and energy shooting outward at 99% of the speed of light, extending for 5,000 light-years from the black hole. This jet is one of the most spectacular examples of how black hole accretion can create directed outflows that influence the galaxy on large scales. When we look at the distribution of black hole masses across the universe, we see a pattern. The most massive black holes, those containing tens of billions of solar masses, are rare. Most supermassive black holes are in the millions to low billions of solar mass range. This distribution might reflect the fact that only the most massive galaxies, those that formed early and went through multiple major mergers, could assemble enough mass in their centers to grow ultramassive black holes like TON 618 and Phoenix A. There's also evidence for a category that some astronomers have dubbed stupendously large black holes, or slabs, hypothetical objects that could reach trillions of solar masses. These would be primordial black holes that might have formed in the very early universe, perhaps from the direct collapse of enormous gas clouds shortly after the Big Bang. While no slabs have been confirmed to exist, theoretical work suggests they're possible, and they might lurk at the centers of the most massive galaxy clusters, their presence difficult to detect because they would be so massive they'd be relatively quiescent, not accreting much matter and therefore not shining brightly. What sets TON 618 apart from many of these other massive black holes is not just its extreme mass, but the combination of mass, distance, and brightness. It's both incredibly massive and shining brilliantly as an active quasar, and it's doing so at a time when the universe was less than a quarter of its current age. This combination makes it an exceptional laboratory for studying black hole physics, galaxy evolution, and the early universe. Mysteries and future observations. Despite decades of study, TON 618 still holds many mysteries, and it remains an important target for current and future astronomical observations. Modern telescopes are allowing us to probe this distant quasar in ever greater detail, revealing new aspects of its nature and raising new questions. One significant mystery surrounds the host galaxy itself. Because the quasar is so incredibly bright, it completely outshines the galaxy containing it. When we point telescopes at TON 618, we see the brilliant point source of the quasar, but the surrounding galaxy remains largely invisible, its starlight drowned out by the glare from the accretion disk. This makes it difficult to study the relationship between the black hole and its host galaxy, to measure the galaxy's mass and structure, to determine its star formation rate, and to understand how the quasar is influencing its cosmic home. Future observations with next-generation telescopes, particularly infrared observatories that can peer through dust and partially separate the quasar's light from the galaxy's light, might reveal more about TON 618's host galaxy. The James Webb Space Telescope, with its unprecedented infrared sensitivity, could potentially detect the host galaxy's stars and study the distribution of gas and dust around the quasar. This would allow astronomers to test theories about black hole galaxy coevolution and understand how a galaxy can support such an extremely massive black hole. Another mystery involves the black hole's spin. We've discussed how the spin of a black hole affects the physics of accretion, the location of the innermost stable circular orbit, and the efficiency of mass to energy conversion. But measuring the spin of a black hole, particularly one as distant as TON 618, is extraordinarily challenging. It requires detecting subtle features in the X-ray spectrum emitted by the innermost regions of the accretion disk, features that are distorted by relativistic effects near the black hole. For TON 618, located more than 10 billion light-years away, the X-ray emission is extremely faint, making detailed spectroscopy difficult. Future X-ray observatories with larger collecting areas and better spectral resolution might be able to measure features in TON 618's X-ray spectrum that would reveal whether the black hole is spinning rapidly or slowly. This measurement would tell us about the black hole's history, about whether it grew primarily through steady accretion, which tends to spin black holes up, or through chaotic mergers with other black holes, which can result in lower spins. The question of how TON 618 grew so massive so quickly remains one of the most important unsolved problems related to this object. Various theories have been proposed, from massive direct collapse seeds to sustained super-Eddington accretion to multiple major black hole mergers. Each scenario makes different predictions about the black hole's properties, its host galaxy, and its cosmic environment. By studying TON 618 and similar early ultramassive black holes in detail, astronomers hope to distinguish between these scenarios and understand the pathways by which the largest black holes in the universe formed. There's also the question of what happens to TON 618 in the future. Both its near-term future billions of years ago from our perspective, since we're seeing it in the past, and its ultimate fate many trillions of years hence. As the quasar consumes the readily available gas in its vicinity, the accretion rate will eventually decline. The brilliant beacon will dim. TON 618 will transition from an active quasar to a more quiescent state, similar to the black holes we see at the centers of present-day galaxies. But the black hole won't disappear. It will remain at the center of its galaxy, a silent giant waiting for fresh fuel. Occasional disruptions of passing stars or minor mergers might cause brief flare-ups of activity, but the glory days of the quasar phase will be over. In the far, far future, billions of years after we can observe it, TON 618's galaxy will likely merge with other galaxies, as all galaxies in gravitationally bound groups eventually do. These mergers might cause new bursts of accretion, new episodes of quasar activity, or they might result in the merger of TON 618 with other supermassive black holes, creating an even more massive object. On timescales that dwarf even the current age of the universe, TON 618 would eventually begin to lose mass through Hawking radiation, though this process would take so long that it's effectively eternal for all practical purposes. A black hole with 66 billion solar masses would take approximately 10 to the 100th power years to evaporate completely. A 1 followed by 100 zeros, a number so large that it makes the current age of the universe a mere 1.4 times 10 to the 10th power years, seem like the I blink of an eye. The stars would have all died, the galaxies dispersed. The very protons making up ordinary matter would have decayed long before TON 618 emitted its last quantum of Hawking radiation and disappeared. Future gravitational wave observatories might someday detect signals from the mergers of supermassive black holes similar to TON 618. When two galaxies merge and their central black holes spiral together, the final coalescence should produce gravitational waves, ripples in spacetime itself traveling at the speed of light. Current gravitational wave detectors like LIGO and Virgo are sensitive to stellar mass black hole mergers, but not to the much lower frequency waves produced by supermassive black hole mergers. However, Future space-based detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will be able to detect supermassive black hole mergers across cosmic time. These observations would reveal an entirely new aspect of objects, like TON 618, allowing us to measure their masses precisely, determine their spins, and understand the dynamics of the merger process in ways that electromagnetic observations alone cannot provide. We might detect the merger of two TON 618 scale black holes, witnessing the creation of a black hole exceeding 100 billion solar masses and approaching the theoretical limits of black hole size. Conclusion: our place in the cosmic story. As we drift toward the end of our journey through the cosmos to encounter TON 618, it's worth reflecting on what this object represents and what it tells us about our place in the vast universe we inhabit. TON 618 is many things simultaneously. It's a black hole of almost incomprehensible mass, containing more than 66 billion times the mass of our Sun compressed into a region smaller than our solar system. It's a brilliant beacon shining across more than 10 billion light-years of space with the combined light of 140 trillion suns. It's a window into the early universe, showing us cosmic conditions from when the cosmos was less than a quarter of its current age. And it's a reminder of the extraordinary progress humanity has made in understanding the universe despite our cosmic insignificance. Think about the chain of discoveries and insights that led us to understand TON 618. Astronomers in Mexico in the 1950s photographing faint blue stars. Radio astronomers in the 1960s detecting mysterious emissions from quasi-stellar sources. Martin Schmidt's crucial realization that quasars were vastly distant and luminous. The development of general relativity by Einstein and its subsequent application to understanding black holes. The construction of more powerful telescopes across the electromagnetic spectrum. The development of computer models to simulate accretion disks and the dynamics of matter in extreme gravity. Each step built on the previous ones, each insight opened new questions, each generation of astronomers passing the torch to the next. And what have we learned? We've learned that the universe is far stranger and more wonderful than our ancestors could have imagined. We've learned that space-time itself can be warped and curved by matter and energy. We've learned that there exist objects so massive and so gravitationally intense that they trap even light, creating one-way boundaries in the fabric of reality. We've learned that these black holes aren't just cosmic curiosities but fundamental players in the evolution of galaxies, influencing star formation across millions of light-years and shaping the large-scale structure of the universe. We've learned that we can look back through time simply by looking outward through space, that the light from distant objects carries information about cosmic conditions billions of years in the past. We've learned that the universe had a beginning, that it's been expanding and evolving for nearly 14 billion years, that galaxies and stars and planets and eventually life arose through natural processes from the initially simple hydrogen and helium created in the Big Bang. TON 618, for all its overwhelming scale and power, is governed by the same physical laws that govern the falling of an apple from a tree or the orbits of planets around our Sun. The mathematics that describes TON 618's event horizon is a direct extension of the mathematics that Einstein developed to explain subtle anomalies in Mercury's orbit. The physics of the accretion disk, while operating in far more extreme conditions, follows from the same principles of conservation of energy and angular momentum that we can demonstrate in a high school physics lab. This is one of the most profound insights of modern science, that the universe is comprehensible, that the laws of physics apply everywhere and every when, that we can understand the behavior of objects billions of light years away and billions of years in the past using tools of mathematics and logic that we develop here on Earth. The universe doesn't require different physics for different realms. The same fundamental forces and principles that shape atoms also shape black holes, that govern chemistry also govern stars, that produce consciousness in biological brains also dictate the evolution of galaxies. And yet, for all we've learned, TON 618 reminds us how much mystery remains. We don't fully understand how such massive black holes formed so early in cosmic history. We don't know how to reconcile quantum mechanics with general relativity in the extreme conditions near the singularity. We don't know what happens to information that falls into a black hole. We don't know if there are limits to black hole mass beyond those we've calculated. We don't know what the universe will look like in the unimaginably distant future when black holes like TON 618 finally evaporate. Each answer we find opens new questions. Each mystery we solve reveals deeper mysteries waiting beyond. This is the nature of scientific inquiry, an endless journey of discovery where each horizon we reach shows us new horizons beyond. TON 618, that distant quasar blazing in the ancient universe, will continue to be studied, observed, analyzed, and contemplated by astronomers for generations to come. Each new telescope, each new technique, each new theoretical insight will reveal new facets of this remarkable object. As you rest now, letting these cosmic thoughts drift through your mind, remember that the same atoms that make up your body were forged in stars billions of years ago.